This work is part of the Cooler Climate Singapore Impact Project and is a collaboration between urban design and numerical modeling. Climate-responsive urban design generally have 5 aspects: the well-organized urban form, greenery, promotion, and highly reflective and cool materials, introducing water and fountains, and application of shading elements. Canwell is the housing facility under the National University of Singapore designated for faculty members. Building arrangement, greenery, and material are studied here to understand, explain, and apply mitigation strategies in a real urban situation.
Hello, my name is Xusheng Huang, working at Cooler Climate Singapore Impact Project as a postdoctoral researcher on urban design in tropical cities. Currently, it is difficult for architects and urban designers to apply the urban microclimate findings without useful tools and actionable knowledge. Our study focuses on mitigation strategies from an interdisciplinary perspective of urban design and numerical modeling to develop the simulation-aided design as a practical method and as a tool for designers to visualize the thermal environment. It could help them to make quick and timely decisions on design changes.
I am Dr. Ming, working as a numerical modeler for Cooler Climate Singapore Impact Project. I developed the integrated urban heat island simulation tool by accounting for major heat sources and sinks in Singapore context. Conjugate heat transfer between the buildings and the surrounding air is solved with the tool by coupling to the normal computational fluid dynamics. It will help urban designers and architects to evaluate the impacts of different design strategies on urban thermal environment. For our case study of Canwell, the simulation date is chosen as December 17, 2012 from 6 a.m. to 8 p.m. The boundary conditions include the daily trade wind from the northeast direction with a speed of 1.65 meter per second. Turbulence is simulated with the standard K epsilon turbulence model. The initial ambient air temperature is set as 27 degrees Celsius at 6 a.m. in the early morning. The air pressure is set as 100,000 pascal. The atmospheric boundary layer is configured to resolve the parabolic wind distribution pattern in the real world. The bottom characteristic roughness length is set as 2 meters.
Building arrangement, the urban elements, building geometry, height and width significantly affects urban thermal environment. Scenario 1 examines 2 basic urban forms, tower and block, and try to understand how to choose different urban forms for the same density. The CFD simulation could help design a specific case. According to the ventilation simulation, wind channels in between the building's cooler zones are observed as compared to the backside of buildings. In regions where ventilation is better and enhanced, convection of accumulated heat will experience lower air temperature up to 2 degrees Celsius. The void deck is popular in Singapore. The study compares the thermal environment between existing case and the new design under the same climatic conditions in order to clarify whether the void deck is a good climate-responsive design strategy to be promoted in Singapore. According to the simulated results, the elevated ground floor has greatly enhanced air ventilation at pedestrian level. The comfort zone is much larger than in the original design, especially in the area with much stronger wind. Substantially, cooler zones can be obtained. As much as 1.5 degrees Celsius of air temperature cooling is observed. The selection of urban surface is important for urban designers, not only for aesthetic purposes, but also for better urban climate. Concrete and glass are examined here as 2 commonly used materials to understand how building facade affects thermal environment. By changing the surface material of buildings from concrete to glass, relatively few differences of wind speed are observed in simulated results, while relatively hotter environment at pedestrian level is observed when the facade is glass. One needs to therefore reconsider the wide use of normal glass facade.
not only because of higher energy consumption for cooling the interior, but also the decreased outdoor thermal comfort at pedestrian level as shown in the simulation. This scenario focuses on greenery as an important mitigation strategy to improve thermal comfort. As the vertical green facade is set with a cooling power of 44.8 watt per square meter, the surrounding air near the vertical green facade is much cooler than the ambient hot air at both pedestrian level and higher building levels. While the wind distribution pattern around the building doesn't change much as compared to the existing case. Oversized balcony is becoming an identity of Singapore's green architecture, where the green vegetative elements and tree planting could supply more greenery coverage for the city and create comfortable vertical public space. According to the simulated results, the air temperature at the balcony has been slightly reduced, although the wind is slowed it down when approaching the tree on the balcony. The surrounding air around the tree is still observed to be roughly around 1 degree Celsius lower than the other hot parts, while the cooling power of the tree is limited to the balcony only.
This study summarizes the impacts of building arrangement, facade material, and greenery on urban thermal environment, which is a collaborative work between a numerical modeler like myself and an urban designer like Xusheng.
As a showcase of simulation AD design workflow, it is proposed as a useful method for research and practice by urban designers.